Hello, discrete math fans. We're going to talk about the universal quantifier. So let's remember that a predicate is not a statement, but when we plug in values for the variables, then we do get a statement. Then it will have a truth value associated with it. For example, we can write down this predicate. X is divisible by 7. That's a predicate because we don't know if it's true or false. We'll turn it into a statement by plugging in x equals 90. In fact, in this case, it turns out to be a false statement. There's another way that we can turn a predicate into a statement is by adding something that we're going to call a quantifier. Quantifiers are words like some or all, and they refer to variables. They're going to tell us how many elements a given predicate is true for. We're going to use this symbol here, this upside down capital A, to denote the phrase for all, and it is called the universal quantifier. For example, we can rewrite the sentence, the square of every real number is non-negative, by writing, for all real numbers x squared is greater than or equal to 0. So we're using this upside down capital A in place of for all. There's another way we can write this. We can specify the domain of the predicate variable by using set notation. For all x in the set of real numbers, x squared is bigger than or equal to 0. Sometimes it's easy to delineate quantifiers using parentheses. For all x in the reals, x squared is bigger than or equal to 0. That's just a delineation thing. The parentheses don't really mean anything. But you'll find later on that this sort of way of writing quantified statements is helpful. All right, so then let's just make a definition. We'll let q of x be a predicate, and D is the domain of x. Remember that the domain is what you're allowed to plug in for x. A universal statement is a statement of the form, for all x in D, q of x. It is defined to be true if and only if q of x is true for every x in the domain. And it's defined to be false if and only if q is false for at least one x in D. And if you can find a value of x for which q of x is false, that's called a counterexample to the universal statement. So we'll be working a lot with universal statements in this chapter. Okay, that's all for now.